Yeah, I forget and I send it at 2 p.m. and everyone's worried now. Maybe there's no workshop. We have tests this week. There's fewer people.
Yes, we are writing tomorrow.
IA. Okay. We're doing a workshop. Yeah. I mean, you're welcome to stay if you want to sit and work quietly, but otherwise, yeah. No. Maybe you'll see some real analysis. Alright. Did we have any chance to look at TUT 8 over the weekend? Okay, so if I do some stuff from TUT 8, we're not unhappy? Yeah? Yeah? So unless we have any other, are there any other requests, by the way? Like any other topics or questions? So we just like look at TUT 8 and pick some stuff from there. I think question 2 was a little messy. It was like this comprehension proof question and maybe didn't have time for it. So I'd like to talk about that. Probably we should do some from question 1 as well. Unless everyone's really happy with question 1. But I'm assuming at least doing 1 or 2 is not bad. Okay, cool. And then, yeah, I think question 3 is a little bit funny. It's kind of interesting. We could talk about it. I don't think it's super central, and we could. Question 4 is quite quick, so we might have a chance of doing, say, 1, 2, you know, some from part A, or sorry, question 1, and then like say 2 and 3. Okay, so let's start. So we're going to do TUT 8, and let's just do some of question 1. Okay. Do we have any particular requests from question 1? I don't know if everyone has the TUT in front of you, but the idea here was we wanted to use the alternating series test on almost all of these. Hopefully that part is pretty clear. It's like there's these -1 to the power k's or to the power k plus 1s or whatever, so we have alternating series, and so we're hoping, we've only really learned one thing to help us treat alternating series, so let's hope that we can just use it over and over again. Any particular requests for parts of
on question 2.
On question 2 or?
Not on question 1.
Oh, okay. Any requests for question 1? Okay, so let's just pick one at random. Let's do like, let's say B, or okay, let's do A. I. Okay, yeah. So let's do like A, D, and I, or something like that. So A, D, I. And you know, if there are any others that we decide along the way. Did you have one as well?
No.
Okay. B. Okay.
C.
Oh, C. Okay. Yeah, C we can do. That's good. So A, C, D, I. Okay. Maybe I should actually write these here. A, C, D, I. Okay. Okay. So part A. We know our alternating series test, so we can actually quite quickly just check whether this series converges. Okay. All we need to check is, so write it down, -1 to k over square root 2k plus 1, and we have a sum from some number, probably k equals 0, up to infinity. Okay, this is definitely alternating because of the -1 to the k, and so we just have to check this other part. So we have to check this sequence ak equals 1 over square root 2k plus 1. What do we have to check? We have to check the AK decreasing and AK goes to 0. Those are, yep.
As k goes to
As k goes to infinity. Yeah, and I guess that that it is positive. But I think we have that right. Maybe I should write that as yeah.
There's a.
No, it's okay. Are you wondering if it's not positive, what happens, or?
No, I'm going to check quickly.
Okay, sure. Yeah, you can check your notes, and then if you still have a question. So, do I need to check these? I mean, so we could say, how would I check that it's decreasing? Well, that comes up a lot, so I'll just give you some tools. So for decreasing, maybe we've discussed this a bit in the course already, but you could just pick an arbitrary k, and you can just check what is ak plus 1 minus ak, and is that less than or equal to 0? So that's one way. Okay. Okay, so this is like ways to check, or you can take a derivative. You can kind of treat it as a continuous function and take a derivative. So you can say f of x equals 1 over square root 2x plus 1, and then calculate f prime of x and check, well, I should really just say it all in one step. Check f prime of x less than or equal to 0. Okay. Now, you could ask me, do I really need to check that this is decreasing for this particular problem? And my instinct is no, but check with the lecturer. So what I mean is, now this is more practical. This isn't like a conceptual thing, but if you're in the test or you're in the exam, you're like, should I spend time actually checking this decreasing, or is it just obvious? Because like we could see, like this just gets bigger and bigger, so the whole thing just gets smaller and smaller. That's a really good candidate for just like stick your hand up in the test or the exam and say, hey, do you want a proof for this? Or because this can take some time. This is annoying to do, but it's actually obvious, and definitely you can carry this procedure out, but don't do it if you don't need to.
Because when you say check a sub k plus 1 minus ak, are you talking about ak or that ak? Because it's...
Which one? What would be the other one? I understand this one. What's the other ak?
It's this one or this one.
Which is this one on the left?
It's this one.
What's the ak here?
It's...
Oh, you're just thinking of the thing that I'm summing down. So I get what you're saying. Maybe we've regularly been writing stuff like sum on j of some aj, but that's just for a particular problem, or that's just a way of like describing it. Sorry, that's a bit vague, but when I write ak here, I mean this ak. Yeah. Okay.
Just absolute value.
Yes.
Perhaps, yeah.
So
You're just worried that often when we write down a series, we write down something like this, and you're saying, do I mean by AK the whole thing inside? No. Because what do we need to check? We need to check whether this guy is decreasing whatever. So when I write this, I'm saying for this guy. In other words, not including the part that makes it alternating, or putting absolute values. Yeah. Okay, and let's just get that away. So for me, I would say if you looked at this and you said, like, AK is obviously decreasing, it's obviously positive, and it obviously goes to 0 without proof, I would accept that personally. But I'm not the lecturer. I don't make the memo, so you need to check. But I'm just saying, if you ever get into a position where they say, like, there's a multi-part question, and they say, please prove that this is decreasing, then this is what you do, one of these two. Maybe you have some other method, but yeah, this is the most straightforward way. You could do some sort of thing with induction and stuff like that. But remember here, you don't need induction. You're just picking an arbitrary k, and you're just showing that this is true, and it didn't matter what k was, so it's true for all of them. Okay. All right. So I'm not going to go through proving this, that it's decreasing or that it goes to 0. Do you want that? Or well, we can. Which one do I want to do? I probably want to just calculate the derivative. Maybe that's my fastest one. Let's see if that goes easily. Or maybe,
Can't you just sub in place of k plus 1 and then k minus 1 and then you subtract? And then maybe it will show that that is less than 0.
you mean doing this method?
Yeah.
I could do that, yeah. I could do either. Maybe we can just do both really quickly. But okay, let's see. So let's check k plus 1. So, all right. So, check. So ak plus 1 minus ak is going to equal 1 over square root 2. I have to put k plus 1 inside here, plus 1, minus 1 over square root 2k plus 1. And then that is equal to square root, I'm going to find common denominator. Okay, so I have 2k plus 1 minus root 2 times k plus 1 plus 1. And then at the bottom, I have a square root of 2 times k plus 1 times 2k plus 1. Okay, it looks a little messy, but do we agree that this is just what happens if I do common denominator? So I just multiply this up here, I multiply this up here, and then I multiply the two denominators. So that's what I've written here, unless I made any mistakes. Okay, and well, this denominator is all positive, so let's just write that down. Maybe this is useful actually, because I'll note you kind of little shortcuts that can get you through this quickly. And actually, it's worth talking about calculating the limits too, because sometimes we're rusty on really proving what's going on with limits. All right, so it's kind of down at the bottom now, but what I would write here, notice the denominator is positive for all k, okay? So that's, this guy down here is definitely positive for all k. So I just don't have to care about it at all. This is never going to affect whether this overall thing is positive or negative. And this is certainly the messier part too that I just don't want to deal with. Okay, so we only need to check that square root 2k plus 1 minus square root 2 times k plus 1 is less than or equal to 0. Okay. And this might be obvious to you already at this point, because this is like bigger than that. But we could check it very quickly. So, you know, these are both positive things. So this is equivalent to just looking at, is it true that 2k plus 1 is less than or equal to this? Okay. I just move it over to the right-hand side. You can always add a real number to any inequality without changing it. And this, everything's positive here, so I can quite happily square both sides. And I just get 2k plus 1 less than or equal to 2k plus 1 plus 1. Okay, and then you can see where I'm going. I'm basically just going to find out, is it true that kind of 0, do I have 1 less than, 0 less than or equal to 1 or something like that?
You get 1 less than or equal to 1.
Maybe 2 less than or equal to 2. Okay.
Yeah.
So we could go back up this way without too much difficulty. I could say, well, 0 is less than or equal to 2, so I can add 2k to both sides. I can add a 1 to both sides, and I get this expression. And then can I square root it? Yeah, as long as I agree that I'm taking the positive square root. Okay, and then I move it over, and I have the thing that I wanted. So we found out that all of this implies that AK is decreasing. Okay? So now we still need to check if the limit goes to 0. That's quite important, actually. So let's...
Can you use the
For the limit.
No, I'm checking if AK tends to 0. I don't know if that's the same
Oh,
thing.
well, I think what you're basically what you're doing there is you can say something like the squeeze theorem, right? Which is kind of like the idea of the comparison test. So everything's positive, and can you find something bigger than it that decreases to 0? But we can go faster than that. That will work. You can definitely always use the squeeze theorem, or if you're thinking of it as all just being a comparison test, that's easier to remember. By the way, we could do the derivative as well, just to check this. So,
The derivative.
yeah, the derivative method. Maybe I'll just show that quickly too, to check if it's decreasing, right? That is sometimes a very useful way. So, just very quickly, all right, decreasing again. Yeah.
I don't remember what the derivative method is.
Yeah, so let's do it.
You did it for first year calculus, derivative method.
Well, yeah, but so we need to feel confident that that it's just fine when we're doing these discrete things. Okay. So there's a big debate. Should a professor stand up in front of the class and say you should know everything from the past? And then every time you have a question about something from the past, they say, oh, but you didn't study, you know? Or should they just do it, you know, like it takes 1 minute? so that's, I lean towards the second. So we want to write down this. This is kind of like the continuous analog of this guy. And if this is decreasing as a continuous function, it's certainly decreasing if I just put in integers for its arguments. So then that sequence is decreasing, okay? The picture for that is something like, if I draw this f of x, and it looks like this, then certainly if I just pick, points, 2, 3, 4, 5, 6, and I make some sequence, you know, a, k equals f of k, if I just plug in discrete points, this is going to be a decreasing sequence if this continuous function is decreasing. So you can feel confident about that. And we can even, you know, prove that, that you can, we're going to accept that always. Okay, so let's find out is it decreasing. So f prime of x, okay, so I have to do minus a half times 1 over 2x plus 1 to the 3 over 2. And then I think I have a 2 in the top too. Did I do this right? Seems right. See, now you say it's first year stuff, but can I do it? So that's also worth considering. So I think this is what I get. Right? And that's less than or equal to 0. So in this case, this was probably actually the faster method, because taking this derivative, it turns out, was very easy. And this is all positive, so you immediately get that it's decreasing. Yeah?
Can I just ask, using this argument you said, can we use maybe strong induction to prove that it's decreasing? Maybe have 2 terms and it's decreasing, and after that assume it's decreasing.
Yeah, you can prove that argument with induction. There's a bit of debate, like, let me just think for a second, if you may not need induction. I think really you can go as fast as saying something like, let f of x be decreasing. So that means, like, I'll just sketch it here. What does it mean for something to be decreasing? It means that x less than or equal to y is equivalent, or implies that f of x is greater than or equal to f of y. Okay? For all x and y that are real numbers. And so now you just say, pick k and k plus 1. Just pick some positive integers, put them in for x and y, and then you get your condition. So I think you could ask, should I use induction? You could use induction. I think it just follows immediately. Yeah. But anyway, so it turns out in this case, taking the derivative was faster. There will be cases where taking the derivative is a nightmare, and you should not do that. And you'll probably just have to glance at it. Like if you see a lot of products of fractions of roots and stuff everywhere, and you're going to have to use the product rule 7 times. Don't take the derivative. hope that the lecture has been nice, and you should do the other method, where you just do ak plus 1 minus ak. And for most of the time, they're going to give you something that there's some way of doing it in a reasonable amount of time. Okay, so we proved very quickly that it's decreasing, or maybe I shouldn't be erasing this part, sorry. I'll erase the older stuff I read. Okay, less than or equal to 0. So now we want to just calculate our limit. We need to show that the limit is also 0. It could be decreasing and its limit's not 0. So we have to worry about that. So we're asking now, is it true that ak equals to 1 over root 2k plus 1 goes to 0? Is this true as k goes to infinity? Well, my favorite way to do this is to, when you have these kind of ratios of roots and polynomials and stuff like that, I want to factor out powers of k, or powers of the index or the variable, so that I can make the denominator finite. So I'll write that just carefully. Goal, rewrite so that denominator is finite as k goes to infinity. This is always going to be quite an easy way to resolve these like ratios of polynomials and ratios of roots of polynomials and stuff like that. Sometimes we forget this from first year and never even learned it. So let's just check. So what I mean by that in this case is I'm gonna factor out a power of k out of this, which means I need to pull it out of the root, so I'm actually going to be pulling out a power of root k. So, am I even lying to you? Let's just think about that for a second. So as it goes, yes, that's what I want. Okay. So what I'm going to say is, I'll just really write it in steps, because in future problems we're going to go faster than this. We'll write out fewer steps. So what I'm going to do is I'm going to write this way, 2 plus 1 over k. Okay? I like that 1 over k, because as k goes to infinity, this goes to 0, and this is going to stay finite. Okay? Then I just need to pull this out of the whole expression. Maybe I'm doing this kind of the backwards of the way I think of it in my own head. Sorry. Yeah, sorry. I apologize for your notes. Actually, the way I do this in my own head is I think about what's the power of k that I need to multiply the numerator and the denominator by to keep the denominator finite as k goes to infinity. So what I do is I write something like this. 1 over root k divided by 1 over root k, and I want to multiply that times this. Okay. Looks a bit funny, but when you do this a bunch of times, you'll see why I'm doing it, and you'll see why it's a little bit hard to write it down, but it's not so hard to think of it once you've done this a few times. And so what I end up with here is I have 1 over root k in the numerator. When this 1 over root k comes inside here, the square root is over everything. So I have this, okay? And then that just equals 1 over root k divided by the square root of 2 plus 1 over k. Are we happy with that? Didn't make any mistakes somewhere? And now we see that taking this limit is very straightforward. I don't have to do L'Hopital's rule. Some of these you can just do L'Hopital's rule quickly, but some of them you don't want to do that. You might, if you wanted to use L'Hopital's rule, it might mean doing 3 or 4 derivatives or 2 or 3. Why do any derivatives? If you can multiply by 1 in a way that makes it so that the denominator is finite, you'll almost never have to use L'Hopital's rule. So you see the limit of this is, as k goes to infinity, is just 0. The limit of this goes to 0, this stays finite, so the whole thing is just 0. And really, if I was writing this down, I'd have to stare at this for some amount of seconds, and then I would start writing down something like this. And then I'm done. I didn't take any derivatives. So just to write that out. Well, so limit as k goes to infinity of ak equals limit k goes to infinity of 1 over root k over limit k goes to infinity of, what did I write here? This equals 0 over 2 root 2 equals 0. Okay? And so what did we learn? So this implies by alternating series test that this alternating series of -1 to the k times 1 over square root 2k plus 1 converges. Because we showed this is decreasing and its limit is positive, and as it goes to infinity, it's...
So, John, would you mark me wrong if I use this argument 1 over square root of 2k plus 1? We know that the denominator tends to be bigger as k approaches infinity, so 1 over k.
Yeah, so the funny thing is actually, how to say, as I said, this is one where it's going to depend on how the question's phrased. If they say, prove in detail this, then that would be wrong. If they say, show us some other important argument, and one of the steps in that important argument is just remarking that something that's sort of obviously decreasing is decreasing, you know, I wouldn't mark you wrong, okay? But I have to go by the memo, so that's why I say you check with the lecturer. You ask the lecturer for the level of rigor or the level of detail. In general, the idea is if we're asking you to do something, focus on that thing that we're asking you to do. So if it's a comprehension proof and they say, show us each of these steps, then we probably want to see like a really rigorous argument for each of those steps. If they say describe why something's true, then they say describe, tell us the story. Just write a sentence, oh, it's obviously decreasing, so blah. But if they say prove, then we want to see something like this. I know that's not the most satisfactory thing. This is why mathematics is not exams. Unfortunately, you have to do the exams, though. So, yeah. Maybe we can talk more about that. That's really a good one. Like, honestly, even you don't have to, you may also say, I don't want to wait till I'm in the test and I'm stressed and I'm just trying to figure stuff out and it's going to waste my time. Go to the lecturer in your next lecture and just show them this kind of thing and say, what level of detail would you like from me? If I see a function that's obviously decreasing, when can I just say that and when do I need to prove it? Okay. Another thing would be something like, so say you have to say that log n is decreasing. Now, are you going to prove that or are you just going to say it? I'm going to argue that you're just going to say it, okay? Like, yeah. Or, well, it's not, I say increasing, not decreasing, but yeah. I know that's a little unsatisfactory, but I think the point is not to check, not to check all those little details. We want to know, do you know the alternating series test? Do you know what you need to check? That's the goal of the question, right? Another thing I would say, sometimes it makes the person marking a little uncomfortable when you, if you tell a story too roughly. So if you say something like, oh, it's obvious that 1 over square root 2k plus 1 is decreasing, and the person marking goes, yeah, that's true, it is obvious. But if you say the denominator gets big and the numerator gets small, the person marking is like, does this person know how to check first year limits? Because maybe they don't, because many people don't. So, you see. So also if you're unnecessarily vague, that sometimes sends a bad message. Rather just say what's true, and then if you need to prove it, and check if you need to prove it. Yeah.
Can you also use the argument that 2k plus 1 is greater than, root 2k plus 1 is greater than root 2k, which is greater than root k, which is greater than k, and then switch it, and then I have 1 over k that side, and I know that 2k plus 1 is greater than 0, and I squeeze k for
Yeah, I didn't check every step, but yes, that's it, absolutely fine. If that's the quickest thing for you, quicker than doing some sort of limit argument like that, then absolutely. But yeah, if you had a more complicated polynomial, like if you had something like, square root k cubed plus pi times k over, product of k squared plus 2 squared times k cubed minus 3.
Yeah, they wouldn't like us if we did that.
True. But you could resolve this extremely quickly with this method.
Oh.
Yeah, I could tell you what the limit of as k goes to infinity of this is
What is it?
quickly. Well, yeah, let's just do it. Let's prove that I'm not lying to you. Is it infinity? Is it 0? Is it something else? So.
I think it's 0. Because the k squared, and then you're going to multiply it with that squared.
Yeah, it's kind of like the powers of k's are bigger in the denominator. And you should have that feel for it. That's also very good to just be like, okay, what sort of roughly do I expect this going on here? But should I write it up?
Yeah, using this thing.
This method? Okay, so what I want to do is I need to make both of these factors finite. So just to be clear, we're calculating the limit as k goes to infinity of this, okay? And I need to, my goal again, saying it in words, was to make the denominator finite. So I need to factor out, or I need to multiply by something that makes this factor finite and this factor finite. So I'm going to guess, well, not guess, I know that I need a 1 over k cubed to make this factor finite, and I need a 1 over k4 to make that factor finite, because I have a power 2 and a power 2. So k4. And so what am I writing in the numerator, just so that I'm multiplying by 1? It's k7. Okay? And this is just equal to, so multiplying through in the numerator, I have to say that I have k3 plus pi k over k14 square root. The 14 comes so that the square root makes this into a 7. And then in the denominator, I'm going to multiply this factor into here. So I have 1 minus 3 over k cubed. And I'm going to multiply this factor into here. And so I have a 1 plus 2k over k squared squared. Okay? And if we had to, the other thing I'd say to anyone, any of you or anyone watching on the recording, work backwards for a lot of these. If you're not sure if you did the right thing here, just, if you start factoring out these k's to get it to turn back to this, is this the factor that you get out? Okay, so there's a limit still here. I'm not going to bother writing it. So what does this go to? Well, let's just simplify it. So limit k goes to infinity. Numerator is 1 over k to the 11 plus pi over k to the 13. Okay, and then what's the denominator just sort of stays the same. Okay, and we'll just write the last step for the heck of it. So what is that limit? It's equal to the limit as k goes to infinity of this numerator is definitely 0. And then as long as the denominator is finite, I know the answer. Definitely this, the limit of this is k goes to infinity. This is 0, this is 1, this is 0, and this is 1. So I just have this equals 0. Okay? And if I was doing this, I also don't have to write all these steps as I get more and more confident, faster and faster with this. So this is an example where squeeze theorem might be difficult. Maybe not. Maybe you could look at this and say I can do it quickly. But this method does work. Okay, so unless there's any other questions, I think we should go back to our TUT. Any questions? So we found out that this original thing we were looking at, maybe people are still writing, we found out that this converges. And now we have to check, we're asked to check, is it absolutely convergent or conditionally convergent? And conditionally just means that it converges, but it's not absolutely convergent. So we have to check if it's absolutely convergent, which means put absolute values there, which means basically this is positive, so nothing changes. This becomes just a 1. So let's write that down. Check. Is sum up to infinity of k equals 0 minus 1 k over 2k plus 1 with the square root absolutely convergent? So that means we just need to look at this series, minus 1 to the k over square root 2k plus 1, which is just the same as, this is always 1 or minus 1, so the numerator just becomes 1 always when you put absolute value, and the denominator does not change. It's always positive. Okay? So we want to check, does this converge? Okay? So how are we going to do that? That's going to be comparison tests, probably. It's going to be our easiest thing. Okay? There may be other ways. So around about TUT 6, we had a somewhat lengthy discussion about how to use comparison tests for these different things where we have ratios of polynomials and square roots and cube roots and stuff like that. But let's just go through it again very quickly. So what do we suspect is true about this? Do we suspect it converges or diverges? We always want to kind of know the answer before we bother proving.
Diverges because k is to the power of 1.
Exactly. So when I'm looking at whatever the overall power of the largest power of k in the denominator and the largest power of k in the numerator is going to give me a hint of whether this converges or diverges. And that's a lot of the exercises in TUT 6. That's what that was about. So we know the harmonic series diverges. That's 1 over k to the power 1. This one is bigger than that, probably. We haven't proven it, but it looks like it is. So it probably diverges. And the reason we want to do this first is because when we're doing the comparison test doesn't give us a hint whether we should be checking whether it diverges or converges. It tells us how to show that it diverges or converges, but you don't want to spend time trying to figure out, is this less than something so that I can show that it converges, or is it greater than something that diverges so that I can show that it diverges? That's going to take time because now you're just looking for like this enormous kind of set of possibilities, okay? What you want to do is you want to kind of guess ahead of time, but in a rigorous or sort of a well thought out way, whether this diverges or converges. In this case, we suspect it diverges, so we know we're looking for something that is smaller than this that also diverges. That immediately guides us to what we're looking for. Okay? So, how did we come to this conclusion? Okay, so just again, we'll see it. We're going to do 1 or 2 more, and then I'll probably make it more clear. But we want to look at the overall power of k, the highest power of k in the numerator, and the highest power of k in the denominator. There's no power of k in the numerator, so we don't really worry about that. And then we're looking at sort of the power of k in the denominator. So let me just write this out briefly so that you so that I can be a little more clear about what I mean. So I'd say something like this. Notice the highest power of k in, and I would say numerator is like k to the 0 equals 1, right? There's no powers of k in the numerator. In the denominator, it's k to the half. I'm thinking of this as being k to the half. I don't really worry about the constants in front of k, and I don't really worry about other terms. I'm just looking for the highest power of k here, which is to the power 1. But then I'm going to say, okay, there's a square root around it. So I'm going to say k to the half. So overall, what I'm thinking is, as k goes to infinity, 1 over 2k plus 1 behaves like 1 over root k, and which diverges. This is the general method, and we'll see this on some other series. But the general idea is I want to figure out, as k gets large, how does this sequence, or the thing that I'm adding up, how does it behave like? What does it behave like? It's the highest power of k in the denominator and the highest power of k in the numerator that dominates. As k gets very large, it doesn't matter. This one affects the sum very little. So we'll see that in some more examples, but the whole idea is that when you're summing the series, it's really as you go to infinity that matters, which will, when I say matters, will determine whether it converges or diverges. It's that behavior from some finite point to infinity that determines whether it converges or diverges. So what we're really saying is, what does this function behave like as it gets very large? Okay, and I'm going to say it sort of roughly behaves like that. You could say maybe it behaves a bit more like that, but that doesn't matter for the purpose of showing whether it converges or diverges. Okay. So this gives me a guide. I think it behaves like this, which diverges, so I suspect that it diverges. Okay, now we prove it. Okay. So, since I suspect that it diverges, I am going to look for something that is smaller than it that diverges. That's my goal for the comparison test. Okay? I think this diverges, this series, so I need to find something smaller that also diverges. If I find something smaller that goes to infinity, this thing also has to go to infinity because it's bigger. So, how am I going to find something that is smaller than this? I need the denominator must be bigger to find something smaller. Okay? I'm not going to change the numerator. So how can I make the denominator bigger? By increasing or decreasing? So denominator must be bigger. So we have to make the denominator bigger. So I have to look at this and make it bigger somehow. Okay? To get something simple that I know the behavior of. Okay? So what I'm going to do is I'm going to replace this constant by something bigger. I'm going to replace it by k. Okay? 2k plus k. And it may seem a little bit magical how I knew to do that, but it's going to come through doing lots of these examples. When I have a constant here, I can make it a bigger power of k so that it matches that highest power of k, and that'll be easier for me to simplify, because you see this is now easy to simplify, this is not. So what is this equal to? 1 over root 3k, or really, particularly, it's 1 over 3 times 1 over root k. Root 3, sorry. And now I've compared this to a function that I know the behavior of by p-series. So I'll write out carefully by p-series 1 over root k diverges, well, this series k equals 0 to infinity diverges. So 1 over root 3 times this series diverges, which implies that sum up to infinity, k equals 0, 1 over root 2k plus 1 diverges by comparison test. Okay. So did we see how, like, sort of the constant in front of the power of k didn't really matter? This little constant we were able to not care about. What really mattered was that we estimate sort of how does this highest power of k behave as it gets large. If you'll notice here, we were kind of estimating that this thing behaves like 1 over root k, and that's actually what we found. It behaves like 1 over root k times some constant. But the point is, if it's times some constant and it diverges, then it still diverges, right? Unless that constant's 0. Any questions on this? Because this is like, in some sense we've seen it before, but it's also a little bit subtle, and we're going to do it over and over, so it's important to ask questions. Yeah.
Here, I just tend to ignore one, say, if that time is greater or equal to 1 over the square root 2k.
But that's not, so I just asked you a question. Is 2k plus 1 bigger than, so we need the denominator to be bigger. So is 2k greater than 2k plus 1? No, it's not. So you can make your argument rigorous if you just messed around with it in a different way. Like, your intuition is correct. But I wouldn't be able to write down this. I would not be able to write down that inequality by just dropping the 1. That would just simply be untrue. But there is a way to resolve, and you and I can talk individually about that if you'd like. Your intuition's not wrong there. In fact, but anyway, I think we won't spend time on that right now. But this is the way I would recommend doing it. If you need to make something bigger, start adding powers of k, higher powers of k. Replace stuff by higher powers of k so that everything matches up. It's all the same power of k. And then you'll always get an argument like this. If you need to make something smaller, start getting rid of stuff, if it's all positive and so on. Okay, so we've done this in like high detail, but let's go through, unless there's any more questions here, let's go on to another one. Any other questions? Okay. And I will say, there was another recording. I actually haven't checked if it was recorded. I keep forgetting to. But there was a recording where we didn't detail a lot of this type of argument. So if you haven't seen that, I'd recommend going back and checking if you think you need more practice. Okay, so we agreed we were going to do C. Oh, sorry, and just to be clear, so what is the conclusion of this question? So we found out the series converges, and then we put the absolute values, and we found out that it diverges. So so we find out conditionally convergent. That's all that it means to be conditionally convergent. It means that the series converges, but the absolute value version does not converge. In other words, it's not absolutely convergent, therefore it is conditionally convergent. So that's what we learned here. Okay, so let's do C. So C was this one. I think K starts at 2. And it's again an alternating type thing over K. Okay, so does this converge? Does it diverge? Does it converge absolutely? Does it converge conditionally? That's what we're asked to check. Okay. So in this case, now through some experience, I can actually tell you that this diverges. Okay, and maybe you can too. And the key idea here is we're going back to that thing where if this sequence that I'm adding up does not go to 0, then it cannot converge. So notice -1 to the k times k over lim k does not go to 0 as k goes to infinity. Okay. And how do I know that? It's really about the way these things are behaving. This k divided by lim k. Okay. And actually, this goes back to the sort of intuition I was describing in the previous question, where I'm looking at the highest power in the numerator and the highest power in the denominator. Highest power in the numerator is k to the 1. And then you say, well, what is that? What's the highest power there? That's kind of a mess. But we do want to have in our kind of catalog of things we know. We want to know how polynomials behave compared to other polynomials. So k cubed is bigger than k squared as k gets large and stuff like that. But we also want to know how exponentials behave and how logarithms behave. Okay, so we have to have kind of in our catalog of ideas, recall, we want to say something roughly like logarithms are less than or equal to like polynomials. So k to the n sum over, let's write it like this, aj k to the j. In other words, polynomials. And those are going to be less than, I won't even put this, exponentials. Okay. And what I really mean is as k is getting large. So logarithms are going to grow way more slowly than polynomials, and polynomials are going to grow way more slowly than exponentials. Okay? How do you remember this one? My sort of favorite way of remembering it. Don't know if I've left you enough time to write it down. Because if you're like me, when I was first learning this, it was very easy for me to remember that exponentials grow faster than polynomials. I heard it a lot in physics, and you hear it a lot in finance and things like that. But how do you remember how logarithms behave? Well, just draw the picture. So you want to compare like k versus log k. Well, you remember how to draw k, that's just a straight line, okay? You remember how to draw exponential, it looks like this, and it goes through 1, okay? And what is logarithm? It's just the inverse function of the exponential. So you reflect it across the line, okay? So which one's bigger between k and log k? It's the fastest way to remember. And then you just keep that like, okay, logarithms of lots of things are gonna be growing less fast than polynomials, because all the other polynomials are kind of, as they go to infinity, growing much faster than just k to the power 1.
What about power functions?
What's a power function?
I don't know if I'm labeling it correctly, like something to the power k. Instead of
Oh yeah, so we're going to put those, sorry, I was a little unclear, we're going to put those in the category of exponential. So the question was about like these, yeah, that probably is the right name for it. I was just like, wait, what are we, yeah. So basically, because you look at like what is a to the k, well it's going to be, you know, the e to the k's and the 2 to the k's and the 3 to the k's. Sure, some are bigger than others, but they're all in this kind of family that's just much faster growth than polynomials. No matter even if you have k to the power 100 as your polynomial, 2 to the power k eventually is just going to skyrocket past it.
So if we're comparing k to the power 100 and 100 to the power k.
Yeah, 100 to the power k will just blow by it quickly. And I encourage you, you can go on Wolfram Alpha and plot it.
Power functions grow faster than exponentials then?
Or I would think of them all as exponentials, right? Because this is just some number to the power k. It's a number between 2 and 3. So this one's going to go a little slower than this one. This one's going to go a little faster than that, because e is like 2.7 or something like that. But yeah, I would think of these all as one family when we're talking about, definitely some are bigger than others, but they're just a family compared to polynomials. That's how I think of it, yeah. That's a good question, because yeah, you don't want to be thrown if you see like 2 to the k. All right, so anyway, going back to this question. So the idea is, I'm just already roughly thinking, okay, well, k over log k is just not going to go to 0, because this just grows much faster than this. Okay. And you could prove that with like L'Hopital's rule. This is a good candidate for L'Hopital's rule. So if I just wrote that, L'Hopital, never remember how to spell this. It's like this, something. K over k is behaving like 1 over k, which equals k, which goes to infinity as k gets large. So that's sort of the sketch of the argument. So this one goes to infinity, this one goes to infinity, but we can use L'Hopital's rule, and we find out that overall, as I was saying, this grows much faster than this, and this captures this, right? This doesn't even go to a finite anything, it goes to infinity, okay? So this series, the terms in this series don't go to 0, and we've always said that you just have no hope of this conversion. Not just you have no hope, I won't stop there. You have no hope of this conversion. All right, so let's, unless there's any questions, we can go on to D. Okay. Excuse me. So D was minus 1 to the k to infinity, k equals 0. And what was it, times 5 over k cubed plus 1. Okay? So, do you have a question?
It's a claim.
A claim. Oh, very good. All right, let's hear.
Is converges absolutely.
It converges absolutely. Okay, so walk me through it.
Take the absolute value.
Wait, first, my first question to you, for our colleagues, why would we go there? Why wouldn't we just check by alternating series tests first?
Why?
Well, you're immediately investigating whether it absolutely converges. Why would you do that first? In the previous question, we checked first with the alternating series test, whether it converged, and then we checked whether it was absolutely convergent or not. Why are you doing something different now? I'm not saying it's wrong, I'm just saying what?
Okay, it's my procedure because I always start with an absolute value.
Okay.
So yes, that's.
So you're kind of like, you know what, let me look at this, which is the same thing as saying, let's not worry about that, let's pretend we had an absolute value. And then if I can roughly see whether this converges or not quickly, all I have to do is check. And then that this converges, so because then if I find out that it converges absolutely, then it converges as well. Okay. So we'll just say, recall converges implies convergence. Okay. This is a type of convergence, so it certainly implies convergence. So I think what you're saying is, well, I'm looking at this, and the powers of k that I see are such that I suspect that this converges absolutely. Okay? Without even using the alternating series test, you could just find out if this guy converges. Whereas if it diverged, like in the previous question, we had to use the alternating series test. Okay? It's a subtle thing. We didn't have to do that, but what you're doing is faster. Okay? So let's do that. So we suspect this converges absolutely and we'll say why. Because 5 over k cubed plus 1 behaves like 1 over k cubed for large k. And we know by p series that this converges, okay, when we're summing this. This is a sequence. Okay, so we suspect this converges absolutely. Okay, so So if you suspect that it converges, then using the comparison test, you need to look for something bigger that squeezes it down. This is obviously all positive. Remember, comparison test is only for positive series, where all the terms are positive. So we are trying to check, maybe I should just write clearly, check this one. This is the result of putting the absolute values around that, okay? And since we suspect it converges, implies that we want to look for something bigger than this, okay? And then I just write this little note to myself. I won't actually write this always if I'm in a hurry, but just to really make it clear, I need the numerator bigger and denominator smaller. In fact, in this case, I won't even mess with the numerator because it's just a constant. So I just write this little note to myself. I find this much faster than trying to think about other stuff. I just say, oh, I need the denominator to be smaller. That's what it means to get something bigger. So how am I going to make that denominator smaller? I remove the 1. Yeah, k cubed plus 1 is definitely bigger than k cubed. So I'm going to make this whole thing smaller, this little denominator, by just dropping the 1. Okay? And this inequality is just true. So, and then we have our conclusion. So, by p series, and the comparison test, sum up to infinity, k equals 0, 5 over k cubed plus 1 converges. Equivalent to saying that sum up to infinity converges absolutely. I'm probably writing a bit more than I need to write here, but I just want to make it really clear to you. You could jump just from here saying by p-series in the comparison test, this converges absolutely. If I'm looking at that, I know what you mean. I know what you're doing. You've shown me all the steps. But I just want to write it in a very clear way when we're first doing this. Okay, any questions on that? So again, the key idea here was we didn't even have to use the alternating series test. We practiced this technique of just looking at the highest power of k in the numerator and the highest power of k in the denominator, and that guided us to guess that we could just jump straight to putting absolute values, investigating that this converges using comparison tests. Okay? The more and more we do of these, the faster and faster that goes, the more we understand. As I say, we practice these techniques also in tutorial 6, so that's always useful to do all those exercises if you haven't done them yet. And to ask questions about them in the tutorials. Okay, so if there's no more questions on that, then we're going to do I. I wonder if there are any in between here and I that are useful.
E, because it has a pictorial.
E.
Yeah.
E is interesting. Okay. Okay, E is a little bit tricky. It's a little bit different from the others. So is H, I suppose.
E is
Are there solutions out for this, by the way? And maybe they come out in a few days at some point. Another claim? Okay, excellent.
Similar to this one, it's converted absolutely.
You claim E converges absolutely. Okay, maybe you can walk us through that. Okay, so that's... So this is also funny because I don't know if you've done the ratio test yet.
Yes.
Okay, so this is actually a strong candidate for the ratio test. So that they gave it to you before we'd learned the ratio test. Okay, so I'll just write like aside a to the k and like b factorial, or sorry, and k factorial, or even it could be a constant. Type questions are natural candidates for the ratio test. And you can see why that is. In the ratio test, you need to kind of like compare k and k plus 1 and divide. And so dividing like k plus 1 factorial by k factorial is always going to simplify a lot. Dividing 10 to the k plus 1 factorial by 10k factorial, 10 to the k factorial, 10 to the k plus 1 divided by 10 to the k is always going to simplify a lot. So maybe we'll show that in a second at the end. They did ask you to do this without knowing the ratio test.
They did?
Well, they hadn't taught you it yet, as far as I know, when they gave you this. Or when did you do the ratio test?
Today.
Right, so yeah. Well, maybe let's just do it quickly with the ratio test. We'll review today. But you could also ask me, how would I do this without the ratio test? So the ratio test is asking us to look at, so I'm just going to say, I'm going to define my, so first someone told us that DeCoso told us that we suspect that this converges absolutely. So he wants to skip doing the alternating series test again. So we're going to investigate this guy, 10 to the k over k factorial. Okay, and ratio test. You need to look at a to the k plus 1 over a to the k, and the limit as k goes to infinity. I think that's right. And that's this limit. Okay. So we have 10 to the k plus 1 over k plus 1 factorial. And
are we doing this using the ratio test?
Yeah. So I'm just going to show the ratio test.
But you said we weren't allowed.
Well, I said they did it, see if you could do it without it, so we'll do that next.
Oh.
But yeah, I kind of flip-flopped in what I was saying. I was saying we'll do the ratio test second, but let's just do it first. So then I have k factorial over 10 to the k. Okay? So we just simplify that thing on the right. These we practice simplifying a lot. Maybe the factorials we don't simplify that often, but you'll need to do some examples and feel comfortable. So I just get 10, okay, over k plus 1. Do you agree with that?
Yeah. That's k plus 1 factorial over k plus 1 multiplied by k factorial.
Yeah, so I'll just write that out, what you're saying. So k factorial over k plus 1 factorial is equal to 1 times 2 times 3 up to k. These all multiply together over 1 times 2 times 3 up to k up times k plus 1. Okay. So all these cancel, and what I'm left over with is just k plus 1. Okay. And you'll get other questions where you'll have like a 2 in here, or maybe a 2 there and stuff. So just be careful about what you're canceling. But otherwise, it's somewhat straightforward. Okay. And then what is this limit? Right. We all agree on that.
Which is less than 1.
Right. Exactly. So, so conclusion. By ratio test, this sum of minus 10 to the k over k factorial, k equals, we probably started at 0 or 1, I don't remember, 0 to infinity, converges. Absolutely. How could we do it without using the ratio test? Do we want to see that? Mm-hmm. There are probably a few different methods. I think someone in one of the tutorials showed me something I hadn't thought of, but I forget it now, so I apologize for that. But there's one you'll see in the solutions, and I'll just explain it a little bit. because it's sort of subtle, but it's a cool argument. The idea is we see something to the power k, so we want to compare with the geometric series. That's the one idea that they use. As we see, the ratio test is much more straightforward for this type of thing where you have factorials and powers, but there are other things you can do. So, another idea. 10 to the power k hints that we might compare with geometric series.
Sorry, will the ratio takes all the root is ever tell you if something converges conditionally? It's usually telling us that it converges absolutely, it diverges inconclusively. So, will it ever?
So if you look, I don't know if they gave you the version for positive or just for any series, but the point is you're always going to put absolute values around it. So it's just going to tell you if it's converging. It's not going to be able to distinguish.
Okay. So if something diverges, you still have to go and try and prove if it converges conditionally at least.
No, if it diverges, then it just diverges.
Oh, because the series diverges.
Yes, yeah, exactly. But what it will tell you, so if you look, I don't know which version they gave you in class. Do you have something else?
It's like if L equals 1, you probably have to investigate.
That's also a thing that could happen.
Okay.
Yeah. That would be, I wonder if you get something like that. That's a good example of that. I'll try to think about it a little bit, but yeah, there also could be things like that. Yeah. But as far as I recall, so I haven't looked over the way they presented in this book, but typically what happens is you either say, we're going to take positive series, and here's the ratio test. And you just take the ratio of an plus 1 over an. Or they tell you take any series, and then take the ratio of an plus 1 over an with absolute values. And that with absolute values is telling you something about absolute convergence. But yeah, I guess we're a little short on time, so I'll think about it a little more. Maybe I can make an announcement. Okay, remember, it bugged me if I don't. Okay, so another idea. This 10 to the k here hints that maybe we can compare with the geometric series. So we know that this is kind of going geometrically, but what do we do about factorial? So in the solutions, they'll give you kind of a cool trick that maybe helps you also practice working with factorials in order to compare this with the geometric series. So what they're going to say, notice, okay, that if I write out 1 times 2, so let's write it this way, k factorial equals 1 times 2 times 3 up to 8 times 9 times 10 times 11 times 12 and so on up to k. That if I had up here, if I instead had like 11 times 11 times 11 for each number that's here, okay, I would find that uh, 11 to the power k minus 10, okay, I'll explain this, is going to look a little funny at first, but you'll see it's a cool argument once we get there, is going to be, I guess we want less than or equal to k factorial. Okay? Now let's just talk through why that's true. So k factorial is the product of all these numbers. Okay? So if I just look at 11 times 11 times 11, how many times? The same number of times as there are numbers in this list, except for these first ones. What does that say? K minus 10. So there are k numbers in this list. I want to multiply 11 times itself, not k times, but k minus 10 times. So in other words, this many times. Is anyone following that? We're following, okay? I want to multiply 11 together. I want an 11 for where there's 11, I want an 11 for where there's 12, I want an 11 for when there's 13, and I want one for each of those numbers up to k. I don't want any 11s for these first ones. Why? Because 11 is less than all these numbers. 11 is bigger than all those numbers. Okay, and I'll explain why we're picking 11, but we're going to get there. So what I claim is that if I multiply 11 together this many times, one for each of these, that is 11 to the k minus 10. K total, but not 10 of them, so k minus 10 times I multiply 11 times itself. Okay? And since all of these numbers are less than all of these numbers, the product of all these numbers is going to be less than the product of all these numbers. Okay? Right? I multiply these all together, they're less than all these. So the product of all these is going to be less than the product of all these. And then definitely if I multiply by these as well, I get this inequality. Okay? Now why am I doing this? Okay. Well, this implies that 1 over k factorial is less than or equal to 1 over 11 to the k minus 10. Okay? And the point here is I have a 1 over k factorial here. Okay, so this is a clever trick to compare a factorial with a kind of a power function. Now, why did I pick 11? Well, you're going to see. The point is, let's just look at this. 10 to the power k over k factorial. You know, this implies, this whole argument implies that 10 to the power k over k factorial is less than or equal to 10 to the power k over 11 to the power k minus 10. Okay? This minus 10 just makes a constant in front of 10 over 11 to the power k. So let's just write that carefully. This makes 1 over 11 to the minus 10 times 10 over 11 to the power k. Just using our laws of exponents. Okay? And this is looking like a geometric series, or a geometric type object. And I chose 11 so that I have something less than 1. You see? And by I mean Neil Robertson. So, or whoever wrote those solutions. So in hindsight, it's all very clever. It's a little bit hard to come up with, but it's just to show you that you see a 1 over a factorial, you can compare it with a geometric series. So let's just write out carefully what's happening. And actually, what is this really? This is just 11 times 10 to 11. Okay? Okay. So altogether, we have that this sum up to infinity from k equals 0 of 10 over factorial is less than or equal to 11 times the sum Okay, I'm cheating a little bit here, so maybe let me not write it this way. Why am I cheating? Because remember, we need k to be bigger than 11.
Yeah.
Okay, so if I wanted to write out really carefully, I can't have k being shorter. It has to be longer than 11 for this argument to work. But that's fine. We know that we only care about with series, we care about large k. So we'll write this for k, for all k greater than or greater than, let's just say greater than 11. Doesn't matter. I could say greater than 100 if I don't want to think carefully about it. And which implies that since 10 over 11 is less than 1, the sum from some k equal to, let's say, 12 up to infinity of 10 to the converges geometric series. Okay. And that just implies that this converges absolutely by comparison test. Okay, so we were able to compare it with the geometric series through this sort of like clever argument. The other thing I'd say is maybe there's a comprehension type question. They show you something like this, and they walk you through it, and they say, why is this true? So that's another reason to sort of know this. You might not have seen it. You might not think of it on the spot, because it's like an uncommon technique. We haven't been practicing it. But, we can work through it and understand it. Okay. We have like 2 minutes left, 3 minutes left. So any questions on this? Otherwise, I might see if there's something I can remark on quickly. Otherwise, we'll be done. I guess you wanted to see I. H as well.
H first.
Okay, I'll give you a quick sketch of H. H we can do quickly. So H is a bit funny because they throw it in here in the middle of all these alternating series. You see it already? Okay, so you're going to put absolute values and, yep, okay. And then I guess, is looking like a geometric series to me. So, but it's k to the k. Interesting. I is a good one for the root test, right? So.
How do you see that?
So the ratio test is one where I see factorials and maybe to the powers. That's useful for ratio tests. How do I see that this is useful for the root test?